So, welcome to everybody for the lecture number 9. So, I present a few files, including this one, which is, so I already presented you this file, is file number 8. So, this file number 8 actually was incomplete. I completed it. Okay, this file was devoted to inductive relation. Okay, so remember, you just have a quick look, quick glance at what we have. So we have our colors as usual, and we define an inductive relation which says to be a traffic light color, several versions. And then we can reason by, okay, and then a binary version, which is a next color, so which represents, in some sense, the set theoretical function from color to color, but which is partial. And then we presented the predicate even, this one, and so we could see a typical proof tree for this type. Okay, and we said that the general shape of a proof tree made of constructors in an inductive type is like this, and then a number of other exercises. So, okay, just to remind you what we have seen, and we could prove, for instance, this kind of theorem which says that for any natural number n, if I have a proof tree for even n, then I can make a proof tree for this relation. And the point is that the proof is performed by induction on this argument, okay, on the way, the possible ways of making a proof tree in this type, okay. So induction even n, so EVN is the second one, the second argument here, and okay, you can go back here so you see what I think. Okay, so we have this, and instead of having an induction on n, which is cumbersome, not really what we want to do, we directly go to the induction on EVN, and we have only the two interesting cases to consider, okay, and so on. Okay, so a case for 0 and a case for successor and successor of n, instead of a case on successor of n, which is not necessarily a good idea. And the same technique was used for reasoning on proof trees of natural semantics later on. Okay, so okay, so a number of exercises such as okay, typical exercises, always the same technique by induction on the ways of making a proof tree. Okay, so that's already you should be a little bit familiar with this material now. We have seen more complicated things than even, but I will go back to this very simple example to show you something new: equality. Okay, so actually I will not show you equality directly. I will go step by step, because if you look at the equality relation in Coq, it's a little bit okay, abstract. It looks a little bit strange at first. So let us go. So here is the second part I added. So the file online start here. Okay, so equality is nothing but a special inductive relation. But we will see that step by step and rather quickly. So first, just remember what is this this type here is traffic light color. Remember, it is a predicate of color on colors with 3 possible constructors: this one, this one, this one, and each of them explains that, for instance, is a traffic light color, orange as well and red as well. Okay, so we are already familiar with this one, and I will consider a simpler one with only one case. Okay, so I consider the predicate, which just says, okay, what is to be green? Okay, so inductive is green with only one constructor, we are called IG is green introduction, okay, which says that, okay, well, green is satisfies this predicate, okay? Don't pay attention to this part. It is just it will disappear soon. Okay. So now, for instance, I would like to prove this very simple theorem saying that for any color C, if C satisfies the previous predicate is green, then C is a traffic light color, something which is quite obvious. And as usual, we will not reason by reasoning by not by case on C, but by case on is green. Okay. So this is exactly what we have. So the thing we already used, but for a simpler predicate. So I have my two hypotheses, a color and a predicate, a proof tree for is green of C. Okay, very simple tree, by the way. And I will say, okay, let us destruct IG as usual. So look at what you will have. You will have actually what will happen is that as C is the only possible. Sorry, there is only one constructor for this one, which is this one. So IG. So we will have this case, and by considering this case, automatically the only possibility is that C is the color green. Okay. So destruct IG will just replace the C by green, and okay, and another side effect of destruct is that the hypothesis disappears. So I will do the same, but with a refine. So maybe we see better what happens, and also I will not have the rest disappear. So the refine will only change the conclusion. Maybe it's easier to see what happens. So I say refine match IG with the only possible case, and here what I will have this goal to solve later. Okay, so you see. So, okay, so this is more stable. We have only this green, which the C has been replaced by green. Okay. Okay. Okay, refine, up, you see the C replaced by green. Okay, and so there is another tactic in Coq for instead of writing all this long line, I just say case IG. Okay, actually, this is a very old tactic of Coq, much older than the destruct, by the way. Okay, so case IG has the same effect. Okay, replacing C, okay, but basically it means it's this refine, nothing more. Okay, and now that's finished. I will solve this goal by saying take the relevant constructor in this in the definition of TL color. So as I don't remember exactly the name of the constructor, I asked Coq to find it for me, constructor, and it's finished. Okay, so nothing difficult, just something which is simpler than what we have done before. Now let us consider the same situation, but instead of this specific green, I will consider an abstract color. Okay, so I enter in a section, and I declare a variable C, which is a color. Okay, and now I have exactly the same predicate as here, except that instead of taking green here, I take C. Okay, so I say, okay, is this color? I call it is this color, which is C. Okay, and same thing. I will prove. This time I cannot prove that because C, I don't know what it is. I cannot prove that it is a TL color, for instance. I could try, but it will fail. So I propose another one. So the only thing I can prove basically is an equality. So, but okay, forget that. Okay, at the moment, just it is the equality, you know, as usual. Okay. So I say that for all x and y, if x satisfies the predicate and y as well, the predicate is this color, then x must be equal to y. Okay, so there is only one solution to this. Okay. So let us take this problem. I introduce all my hypotheses. Okay, you see them on the right-hand side as usual. Okay, and now same thing. I will reason by case on what are the possible proof of ITC-X, and then what are the possible proofs of ITC-Y. Okay, so let us first take the first one. So for the first one, I use the long expression, the refine. Okay, and you will see that X will be then replaced by C. Okay, because it is the only possible case. Okay, so X becomes C. Okay, so and Y is not touched. And now for the second one, I choose the short version of the same tactic, for the same, yes, the same program. Okay. This time Y is replaced by C, and I can conclude by reflexivity. Okay. Okay, so one additional level of abstraction, and let us go to yet an additional level of abstraction. By the way, I can print what I get. Something I didn't show to you, actually, when you leave a section, what you have defined is not lost, actually. It's not like a module, but all the things which were defined, actually, could depend on this variable, and the fact that they depend on this variable will be implemented by the fact that it is now a parameter of your definition. For instance, let us print is this color. So you see that is this color. It is now an inductive, like before, with you see color row prop, like here, and then you see the definition itself, the inductive definition, it is here, like before, okay? But the difference now is that you have, the only difference is that you have this additional parameter here, which is a color, see the color, okay? So, okay, yes, we don't see everything actually. Yes, here you see everything. So you see, you have this parameter here, and you see that to be, is this color, okay? So the parameter is repeated here because it is a parameter of is this color, okay? So you have this instead of just is this color before here. And the second C that you have, that you see here, corresponds to this one. Okay, just to see that what we have done. Okay, so again, an additional level of abstraction. Instead of talking about colors, I will talk about any type. Okay, so is this thing, I'll call it, not is this color. So I introduce an arbitrary type A. Okay, it could be a set, prop, or all type. Okay, I don't care. Okay, some type A, and then instead of C, which is a color, I have X, which is of type A. Okay, and then exactly as before, exactly the same definition here. Instead of a color here, I have an abstract A at this place. Okay, and exactly the same as before, and I can repeat my previous theorem for all. So I call them A and B. If A is this thing and B is this thing as well, then A is equal to B. Okay, so both of them should be X. Okay, so the same. So our variables, the two hypotheses, and then I will reason by case on ITC, then by case on ITC-B. Okay, ITC-A. So you see A. The only possibility is that A is X. Second, sorry. Here. So I go back. Okay, so first possibility. Okay, so A must be a X. Okay, B must be X. Okay, and then reflexivity as before. Okay. Let us see what we have at the end. So basically the same as before, but we have this time two parameters: an abstract parameter for A, a parameter for X, Okay, and this is the property of X. So it means to be this X, okay, in some A. Okay, and okay. Nothing. Okay, so now let us make a simple experience. Let us print EQ. Okay, but it's the same. Actually, I have just another. I renamed. I provide the definition of EQ but just with another name. So equality in Coq is basically an inductive type, which means for its second argument to be the same as its first argument, which is a parameter. So when you see the, okay, sorry, the difference, sorry, is that you have a notation here, but actually it means EQ X X. Or EQ applied to A, applied to X, applied to X if I want to be complete. But you see that, so this is why this definition is a little bit more complicated. It cannot be the very beginning. You see that A is an implicit parameter, otherwise it is impossible to use this as a binary. Actually, equality is a ternary relation. It is a relation between a type, an element of this type, and an element of this type. But okay, using this trick to have implicit parameters, then we can use an infix notation, which is the usual notation. So, okay, so equality basically is something you know to use it. Intuitively, it works, but it is not a primitive notion of type theory. It is something which is defined using an inductive relation. Not that complicated, but a little bit abstract with many parameters, as you can see. In particular, you can see that EQ is not the smallest reflexive relation. The name here looks can be a little bit misleading. The other possible definition would be something like this. Inductive. Okay, it's a little bit. Okay, I will go to this place because I don't want to have so many parameters. I could go here and say something like inductive. Okay, EQR. Let's just go to equality in A, which is the thing that you would have in mind actually at first. So it would be something like this. Not with 1, but 2A. And then you say something like, okay, EQA is reflexive, which say that for all X of type A, then EQA of XX. This would be in some sense, the smallest reflexive relation. Okay, so this is different in Coq. The choice is different for some good reasons. Actually, the first is made a parameter, and the second varies. So it makes things actually much more easier to. You can try to play with that if you want. Okay, it's not something so important, but if you play with this one, you will see that. Okay, you can prove a number of things, but at some point you get you don't exactly have what you want. The point is that what you want with equality is to have the Leibniz principle which says that for any elements x and y such that x is equal to y, if you have P of X for any P, then you have P of Y. This is the principle you want to have. And this is not the one you get with this definition. Okay, so I can keep it if you want. So if you look at EQ, okay, we have it. So this principle, which is derived, no, I will do first because it's too much information. Just check to understand. So it's enough. So, okay, so if you look at this principle, it is exactly what you expect for equality. You have, so your parameter A, you have an X, which is given, and you have a property, and you say that if you have P of X, then for all Y such that X is equal to Y, then you have P of Y. Okay, this is exactly the Leibniz principle. If you do the same for is this thing, ind. So the ind is, you will see that later. So you see exactly the same with the longer names. Okay, but you see again, if I have P of X, then for all way, if I have this thing, so here the parameter is not implicit, so I can see it. If I have this thing, sorry, for A, then P of A. So exactly the same Leibniz principle. And if I look at the previous one, so I called it EQA, ind. So the other one, but you see something different. Which okay, so you can look at it, but it's not. So you may ask where does this int come? Okay, actually, each time you define an inductive type, Coq provides for you an induction, what it is called an induction principle or an elimination principle in logic. So that's printed so to see how it is defined. So it is a little bit complicated to read, but so you see that basically what you have is this match. So it is a little okay. Don't waste too much time to read all this part. But basically, what you see is that you have exactly this match E with the constructor, which is exactly what we did before on the left here. Match the thing you want to consider, match your hypothesis with the constructor. Okay, so this is match the thing you have with the constructor. Okay, so basically this elimination produced automatically produced by Coq. So each time you define a list or whatever, you can. Oh yes, you can do that. For instance. Maybe we never did that. Print, for instance, an at ind. Okay, the induction principle on not natural numbers. Okay, so let's in two steps: the check and the print. It's interesting. Check. Okay. So here you see exactly the usual induction principles on numbers. So you see that you have any property on natural numbers. If you have P of 0. And if you have, if you have here, you have to be slow. Okay, and if you have P of n implies P of Sn, okay, then for all n, P of n. Okay, so this is, and the point is that this principle is not given as an axiom for free. It is actually a consequence of type theory, in the sense that it is a program. So if I see it as a program, so I get exactly the type, the same thing as the type, but you see that this program actually is a fixed point. You see that it is a fixed point. Okay, so it's reasoning by a recursive program which performs filtering on n. And then if n is 0, you return the basic value for 0. And if your n is the successor of something, then you apply the second function applied to n0, and you make the recursive call here. Oh, okay. It takes your time if you want to read that, but there is nothing more that all what we have seen before, just by intuitive reasoning. Okay, and that's the same for lists, for binary trees, etc., etc., etc. And the same also for inductive definition, such as even or such as EQ. So okay. So EQ ind is defined in the standard library. You have also EQ sim, which is which okay, or maybe okay, there is a proof, but maybe what is more interesting is the just the type, which says that it will just say that if x is equal to y implies y is equal to x. Okay, the proof it is a simple exercise to prove it, and the point is that you have also, or maybe no need to. Okay, the print actually the EQ in R is programmed with the previous ones. It is why I printed it. Okay, but so this is the reverse of before we had Px implies if x is equal to y, then py, and for this one, it is the reverse direction. It is if y is equal to x. So the only thing you have to know is that when you when you use the tactics rewrite with an arrow to the left or without, etc., it just use one of these programs, EQIND or EQINR. Okay, so what we started with actually was using these somewhat abstract definitions, quite intuitive for the basic usage, but just to see that actually there is nothing nothing predefined. I mean, in the underlying theory, it is just an application of general principles of type theory. Okay. So so that's all for equality. Now, okay, so this is the conclusion. Just the only thing you have to remember from the practical conclusion. Okay, then there is a third part I will present after. Okay, so now I will talk about other things, including extraction. So I consider now, I go to this file. So now I consider the file which is called if you are, it is on the website, sorry, Coq 1 Theory 4. So not in it because this is not an introductory part. Okay, this one. Okay. So I will introduce a somewhat advanced topic, but as usual, I will present it on very basic and simple examples, and as usual, my colors. Okay, so we can paint many things with colors. Okay. So what I want to show you is how to define so-called partial functions in Coq. So partial, okay. Here, usually when I pronounce function, I mean functional program. Okay, so each time you talk about something which is of type A, arrow B, it is not a set theoretical function. Okay, it is a first intuition, but it is sometimes a bit misleading. You know that when we talk about update and get. Okay, but A to B is the type of programs from A to B. But okay, here I don't have another name to talk about partial functions. So okay, so I just have this footnote saying that okay, in this here I'm talking about set theoretical function or function in the extensional sense. I could add so maybe, not sure. Like this, okay. Okay, so let us consider our set of colors, set enumerity type. Okay, So yes. And then, okay, so I have to make it bigger here. And then our binary relation, okay. Yes, okay. So my aim for this part of the lecture actually is to define some function corresponding to this specification. So the point is that you can see that this specification is for partial function. It is defined only for green, orange, sorry, for red and orange, but not for the other colors. Okay, so how to define this in Coq? Not obvious. Okay. Okay, so I first start with an inductive type. So here I use the sort set because I want to show you something. Okay, so I consider this type, which says to be a TL color, but now it is seen as a data, not as a property. Okay, so it is exactly the same from the type theoretical point of view. It is the same, but in the universe of sets of data, not in the universe of blah blah. I would say the propositions. Okay. Okay, and you see that I can define actually something. So I can define this function, the function next color, which is C, the color C, and another argument called the T for traffic light, which says that T is a traffic light color in the set, in the sort set here. And I just make pattern matching on this one, and it works. So T has three possibilities: this one, and that one. Okay, here, there, and for each of them, I return my answer. So for me, it's orange. So okay, it looks fine. I think it is probably the thing you would define in Agda, another proof assistant which is quite close to Coq, but we does not have the notion of prop. You don't only have types or sets type, this kind of thing. Okay, so you would. What I say now is that it is not what you have in mind. Because, okay, so I will show you, I will present you later in more detail what is extraction, but okay, just to show you, if you try to simplify in some sense what we have defined here, so I will not define this in the rich language of type theory, but in the somewhat poorer language of OCaml. Okay, so a language which has also a type system, but without dependent types. That's the point. So it is possible. So Coq offers a mechanism called extraction. So we will be much more specific on that later. But at the moment, just remember that with extraction, it's kind of translator from Coq to OCaml. So to some extent, okay, this mechanism exists, this translation, this compiler. Okay, so I need this command first, and then I have this command here. Oops, sorry. I say recursive extraction. Recursive just means extract not only the function here, but also all the other definitions which are necessary for defining this one. Okay, and here we see the result. So this is something which is very close to what we have here. Yes, so we can see the translation of color in OCaml. Okay, so okay, so in OCaml we don't have to provide the type; we just enumerate the values. Okay, is TL color? It is this one. So what you can see is that the argument here has been cancelled. Okay, erased. Okay, so it is erased, but for the rest, we have something which is okay, similar. So T gray, T aura, and T red are the three constructors in this type. Okay, so translation just amounts to removing this parameter here, this argument parameter. And then my function here, it takes two arguments, C and T, okay? Okay, so this is, okay, you can see the type in OCaml. So the presentation, actually, it's what you have to know to understand that is that function in OCaml is a short for fun. What did I write? No, I cannot write. Okay, so okay, I will just copy it here. So in comments. Okay, so if you write it in a way slightly longer, it is like fun T. So the arrow of OCaml is like this, and match T with it is just like this. Okay, this is exactly the same meaning. Function is just a shorthand for fun blah blah arrow match this blah blah with. Okay, so if you now compare with our original coq function, you see that, so here we have actually an argument here which is not used, so we could name it to see it more clearly. It is actually C, but you see that C, okay, it is just something which is unused, and then the pattern matching is just against T. So what we have here is not what we wanted to have. We wanted to have a function from C which is only defined for some values in this type, okay? And actually what we get at the end is something which where the original color is not used. It's just something without interest. And okay, so we have actually this real thing which is used. So this is not what we have in mind. What we have in mind is something like I would like to see something like this. Match T with, and here I would like to see, for instance, what are the value purple. Okay, okay. What I would like to see is that this one. For green, I want to see orange. For orange, I would like to see red. For red, I would like to see green. And for all other cases, okay, okay, something saying, okay, okay, fail with, something like this. Fail with, not allowed. Okay. An exemption saying that the other cases are not relevant. This is what I would like to see. So this is basically the information, the function I would like to define at the level of coq, something which really considers C, but T is just a sign of a kind of comment. And okay, after all, T should not even be considered. So maybe something like this. We will see later what we want exactly. Okay, maybe actually it is not used, so maybe we don't need this one. Maybe we just want let function. Okay, this is enough actually. Okay, this is what I want. Okay, the second one is not relevant. It is just a comment. So we will learn something new, which is that we have the good mechanism for doing that, which is instead of using set, like in Agda, using prop. So this is actually what we had before. Our first definition of is tail color was a prop. So you can see something which is similar in its structure. It is also for making proof trees or trees, some trees, data trees or proof trees. Okay, but I want to say that actually, okay, it is like a comment that it is useful for me, but I don't want to program with it at the level of data. Okay. So actually, if I try the same definition, so it is, you can see, I can show you what I defined here. This, yes, this one. Okay. So you see that this code here and there are exactly the same. Okay. The only difference is that now STL color is a prop, while before it was a set. Okay, but the code is the same. And Coq will not accept it. Let us see the message. Coq answers incorrect elimination of T in the inductive type STL color. The return type has sort set. Why it should be okay, prop, and there is another one similar which is called S prop. I will not talk about this probably. Okay, so what's the important thing is that elimination of something of sort prop is not allowed on a predicate in a sort set, I think, or type, something like this. Yes, in sort set, because proofs can be eliminated only to build proofs. So what does it mean? It means that what we did before, we were able to reason by cases on a proof tree, but it was always to make another proof tree in another type. For instance, proving that even of n plus m from a proof of even n, this kind of thing, or proving things about natural semantics. Okay, so we can do the same. We can program with proof trees and make new proof trees if we are in the universe of prop. We can make case analysis on data to make data, that's it's allowed as well. We can also, proofs can see data. I can, for instance, reason on the colors to get a result, a propositional or predicate on some color, that's allowed, but there is one direction which is not allowed, it is exactly this one, it is to use a T to use the contents, the information content in T. So T should be one of these three cases. I cannot use this information to make a data. This is the basic thing. And actually, this is the only mechanism they have in Coq between prop and set for distinguishing these two universes. Okay, so what can we do? Okay, so this is the lesson. Pieces of information available at the level of propositions are not available at the level of data and programs. Programs for okay. Okay, so in order to we will use inversion and as you already know small inversions. I just defined the small inversion principles for this predicate. I will need it later. Okay, so just for you to remember, but otherwise just remember we in order to invert something we will use this. Sorry. So. See if you want, okay, maybe I can see, okay. Okay.
I have a question here. So
yes.
What is different functions? Is it better to use an option type?
An option type is not always sufficient, because if you have an option type, it means that you can define a number of partial functions with that, but not all of them. In particular, if exactly the thing we will go later, if the domain is undecidable, you cannot use the option type.
No.
So you can use option type only if you can decide in advance. If you okay, so typically, so a good example typically is division. Euclidean division. You want to divide A by B. Okay, you know that Okay, so you have a general program for that. Whatever A and B, even if B is 0, you don't care. Just say, okay, in order to divide A by B, I just repeat subtracting B to A until I get something smaller than until you get to 0, something like this, okay? But so it works as far as B is at least 1, because then A diminishes, okay? Okay. And if B happens to be 0, you go to an infinite loop with this program. So usually what is done is to, before entering the loop, you check if B is equal to 0. Okay, so it's like you not use the option, but it's the same idea. Okay, in that case, we have an algorithm for deciding in advance if I am in the domain or not. Okay, but it's not always the case. Okay. In particular, you cannot use that for making the program for the denotational semantics of while. Very perfectly undecidable case. Okay, so let us go back to this technical thing. So as usual, I have my type here. So I define is green. By the way, it is exactly the same of I used at the beginning of the lecture. To be green, to be orange, to be red, and to be something else. Traffic light color other. Okay, okay, and then the dispatch function. Okay, you can prove that if you have a color C such that C is a traffic light color in this sense with a prof, then okay, you have dispatch and you can use it. Okay, so let us go to this point. Otherwise, just use inversion. But this one is okay. We see better what happens with this explicit definition. So small definition. Now, the next big thing. So I have two ways of defining it for defining it. One is explicit and one is with a script. So okay, so I start with the explicit one. So exactly what I want. I take a color C, a function of C, and then a proof tree saying that C is integral color. So I am not allowed to make a pattern matching on T at this moment. So what I want to do is a pattern matching on C, on the original color. And I say that C can be green, it can be orange, it can be red, and it can be something else. Okay. Now the tricky things. Now the tricky thing is that I don't return color immediately. Actually, I will return is color implies color. Okay, so this one. So I say that what I return here is the full type here. I return a function. You can see that in programming side as a function which takes a proof tree here and which returns a value, a color. Okay, and so each time I have a function, so T will be of this T, for instance, will be of type is TL color of green, but I don't use it. It is here, but I don't use it. Here, T has the type is TL color of orange, T or red, and this one it is the one which allows me to see the other cases, the partial part. It is here. So here T will be one. Okay, is TL color of yellow or of green? Also one of them. So I actually with this single line. I have four lines actually, okay, one for each color. And what I say here is that in that case I will return this thing. So we will see exactly what it is. But the point is that I compute this thing, and you see that I am in the other cases. So in the other cases, its type will be this one. So it is an inductive type with no constructor. So there is nothing to consider. So logically, you see that it works. Actually, there is a caveat here, but okay, I will say it. So at the moment, okay, you can see that this one will be accepted. Okay, and maybe so the other way. So the two ways have their own interest. So here we have the full code very quickly. Okay, and don't forget to apply this to T because T is here. Okay, so this part of the code return a function. This function has to be applied to T. Okay, so a little bit complicated, not that long, but okay, you have to be careful. Maybe the script mode is or interactive mode is easier to use. So let us see what we want. So I just state the type of my function. It takes a C, a T, and it returns a color. Okay. Oh, sorry. Place. Okay. So I have my C, my T. I want to make a color. So I know. So destruct T would not work, of course. Case analysis on source set, blah blah blah. Okay, always the same thing. Okay, but this is not the right thing to do. I will just make my case analysis. So destruct, remember, the destruct will actually take the possible value of C, not only in the conclusion, but also on the hypothesis. So Coq will make a revert and an intro. So the revert is here. No, sorry, the revert is here and the intros are there. Okay, but okay. So destruct does this automatically for you. So let us say okay, I have this one, but now I have not 4 cases to consider for a single case like this. But I have all my 7 cases to consider. Okay, but let us do the work. First case, purple. Okay. Then I say that I can just do this. It's finished. So if you want to see what happens, we can check once again what it is. Oh, you don't see so many things. But you see that it is STL color dispatch purple, but let us compute. If you have dispatch of purple, you get STL color of other, which is just, once again, it is just this definition with 0 cases. So let us continue. So this one is here. Next one, indigo. Same thing. I can remove it. Blue, yet another empty case. Now I have green. So I have to return a color. Here I have to be aware of what the function I want to write. I don't want to return any color. The right color to be returned here is orange. So I say exact orange. Yeah, okay. Now I have a yellow. Oh, yellow is empty. Okay. For orange, the answer is red. And for red, the answer is green. Define. Okay. So it was a little bit dangerous because here I chose orange, red, and green, but maybe I could have made another choice. It could work as well. I could, for instance, here put a green or yellow or whatever. I would get a function with this type. So what I want is to be sure that the function I defined satisfies the predicate next color. So it is stated like this. I say that for any color C, such that okay, I need this argument because I want to apply my function script, which is dubious here. So I have to apply this function to order to get a color, and the color, this output color should be the output, the second argument of next color. Okay, so next color of C, the input, and the output here. Okay. So let us prove that I did not make any mistake. Proof. So here, now it is a proposition here. Next color, remember, it is in the sort of next color is prop. So I could, like here, make a case analysis on C, but I am also allowed to use T directly. It will be shorter. Okay, so here I can make a destruct T. I could not make a destruct T here because I was defining a function in the realm of sets, but now I am in the realm of props, so I can make this one. Okay, so let us destruct T and like this. Okay, so you see that in each case, the function can be computed. For instance, the descript green and this constructor here. So let us do a CBN. So I have to prove next color of green and orange, which is the result of the function. By the way, it was defined here. Okay, it was at this place. Okay, so okay, so let us. Sorry, not here. Here, I just want to. Okay, so I destruct. Then I compute. You can see that I have the 3 goals, which looks fine. If I put here a yellow, for instance, here, yellow. Okay, I define it. I try to fool my theorem. And here you see that I need to prove this one. Well, sorry, we use the all. I need to prove this one. It will be okay, but for this one, I will not be able to prove it. Okay, so it is always good to prove some theorem. So let's go back here and have the red answer. Okay, it looks fine. So now I will at once make my proof, destruct, compute if you want, but constructor should do the. So this is the constructor of the next color. It is the next color which will be used here. Okay, finished my proof. Okay, now another interesting alternative, which is to at the same time define a function and prove its correctness. Okay, so its correctness will be here defined by an auxiliary predicate, which is defined in this way. Not a predicate, sorry, with a rich data type. So this is something we can, okay, we use yet another use of inductive definitions with, okay, with parameters and so on. Okay, let us read it. So I define the specification of the next color of C, and I say that it will be a data made of 2 parts. First part, some color C prime. Second part, a proof that C and C prime are related using the next color relation. Okay, so this is my constructor. I have one constructor which says that, okay, for any C prime such that blah blah blah, then I will have an inhabitant of this type. Okay, so it is, so there are pairs, and now I will define a function with the same inputs as before, so a color and a proof that this color satisfies this TL color, and I will return here not a color but a color decorated by a proof that next color C prime. So a color C prime such that, okay? So exactly the same script as before, but you will see that now I will not have the choice at this stage. So let us see what happens. I will put this on the top, okay? So interactive again. destruct C. Okay, so the first cases are similar. Purple, there are 0 cases. So let us continue. Second case, indigo, 0 cases. Blue, 0 cases. Here the new something new. Here I have to provide an inhabitant of next color spec of green. So I have to provide a color plus a proof that this color satisfies blah blah blah. So I will say I use this constructor here, NCNK, which with the first argument, which is the original argument green, okay, and the answer is here, orange, okay. So remember, this constructor has actually 3 arguments because we have this first argument, which is the parameter of the definition, and then the real answers. This is the output, orange, and here I have another one which is not specified here. I could say maybe, or maybe it's more clear with a refine. Okay, and okay, here something saying that I will need to provide a proof of the last part of the constructor. Okay, so imagine that here I say no other choice. It can only be orange. Suppose, for instance, I try blue. Okay, until here it works, but now I have to provide a proof of next color green blue. I cannot. Okay, I cannot provide this, so I'll backtrack. Now I will say orange. And now I have a nice goal to prove. I can prove it by the constructor or seeing exactly which one it is. Let us show the proof. So you see, okay, so we have the first cases, purple, indigo, and blue. In each case, okay, we have a match with N, okay. Where we are is here, okay. So we take a proof of this. Well, it is not used here, it is used in the other cases. But the point is that now we have NCMK of green, orange, and here we have the constructor here, the tactic constructor found the right constructor in the type next color. It is called CSV. Okay, and for the other ones, I have things to finish. Yeah. Sorry, I'm too fast. So here it is for yellow. So for yellow, 0 cases to consider. And now, okay, so here I say, okay, refine or okay. I just say that here the first argument I'm not mandatory to specify it because actually it is it can only be orange. Okay. I could use also refine, prefer, more clear, I think. Okay, constructor, and another possibility is to use another tactic of Koch called exist. So exist actually means constructor, but it you add arguments saying here, yes, because I think let me try constructor. I think Koch will complain saying that but I need some information, some additional piece of information. Yes, unable to find an instance for the variable C prime. So I need to provide the C prime. I wonder if green would work here. No. Okay, so you need to use say a more advanced. Okay, this is not only constructor, I think. Exist actually works only when you have a type with exactly one constructor. If you have 2 constructors, I think exist is not accepted. And exist has parameters. You put here the values which cannot be guessed from the conclusion. So here the red, we have it. The red is a C, but okay. So I just say exist green, and okay, I finish the proof. Okay, so here I have another version of function next color, and I added CBC, which means correct by construction. Okay. So I can do the same as before. It was purely using a script. Here I will use the refine tactic in order to manage all the other case in the same way, okay, like before. So I will say refine. So again, so exactly the same thing as before. I return a function from STL color to here. Before it was just a color. Now this one means next color spec of C. Actually, I could put it. I was lazy. I just the important was to add this information for coq, and then as before, I will. So I return a function which has to be applied to T, and T is an argument here, and in the void cases like here, so I just match the inversion of T with 0 cases. And I'm left with the 3 interesting cases to be filled. So what is the answer for orange? What is the answer for red? What is the answer for, sorry, not for orange, etc. And yes, so for the first one, constructor. For second one, constructor, and for the last one, actually here, I didn't provide the NCM key, so okay, I can provide it. Okay, just variations on the different way. The point is that sometimes the refine technique is interesting because you can with it finish many goals which are similar, many empty goals in that case. Okay, and then you can compute it. So for instance, I can compute, so this function which is called by apply to orange, and the proof that orange has this sorry, what it is here. This is a traffic light color. So the proof that orange is array. Okay, and what I get is an answer which contains the red plus okay, something else saying that red satisfies the post condition. Okay. Yes, you can see actually. Yes, the interesting thing is that you can see this definition like a function from an input. Then you have here a precondition on this input, and this is the output with its together with its post condition. Okay, it's interesting. So here we see the result. The result is the output with the post condition. So usually you are as a programmer only interested in the output. So let us define the function result of an X color, which takes so a color, a precondition T, and then I compute my function on C and T, and I will just return the first part. So coq has this construct, which is the let construct, which works when so the condition is that the result type of this should be an inductive type with one constructor. So it is the case. Let us see. Here, you see that is here you have only one constructor, and we can decompose all the elements of this constructor. So here we have only we have 2 of them. We have C prime and C. The other is an argument also, but it is not. It is a parameter. It's not the same. So so I am here. So I say let C prime, and this is a placeholder for the post condition, but I don't want to use it, and I just return C prime. Okay, so this is a camel-like notation. Which is this one, it's not at the right place, it should be here. Okay, so I compute now this new function, okay. Oh, sorry. Excuse me, I was not at the right. Okay. So we'll see that later. So excuse me, so I compute this one, I return C prime, I compute my function applied to a color and a precondition, and this time I get exactly red as expected. Okay? So now, what I can do is to prove that for any C and T, which is okay, we find that C has type color and T has the type of the preconditions. Because of this use here, I want to prove that C and the result, exactly this function here, the result obtained by applying my function and keeping only the color part, okay, satisfies the relation X color. So I have my relation between C and the simple output. Let us call it like this. So the simple output, and so the proof is very simple. Once again, okay, so let us unfold this definition here. So we get exactly our let C, etc. And here I don't need to make to reason by case or on C or on T. No need. I only need to say, okay, I need only to reason by case on this expression here. Okay, so I say that this expression here, f function next color of CT. Okay, this function return a pair made of a color and post condition. Okay, so I will return the two parts of this type. So after decomposition, I get the output color, whatever it is, and automatically, so this is actually by the very mechanism, no, by the very type of the result. It is a rich type with a color, and we know that it is the result is a pair of such a color and a proof. So the proof, it is exactly what I want. Okay, so it just means that correctness by construction works as expected. This is something very general. Actually, each time we have this kind of type, we have this type this. So actually, Coq contains a general type, which is called a sigma type, or sig for short. Okay, so sigma, it is a name used in type theory. So let us print sig, and you will see that sig is just a generalized version of our type, which was defined here. Yes, next color specification. Okay, it is just a general version of this type here, but more abstract. So we have a type A for the input, a property on the input P, and instead of our MK something, which was here, instead of NCMK here, we have a constructor called exist. So I would like to yes, okay. So we see everything. So the constructor is called exist. Oh, that's it. The name chosen by in the standard library. And again, instead of a for all C prime here, we have a for all X of type A, P of X, a proof of P of X instead of a more specific property. And okay, and that's finished. Okay, so an inhabitant of sig sig P, sig AP. So this is a notation for this one. You can see that, okay, it is a set theoretical notation, but it's a little bit misleading. It is intuitive, but you have to take care. This, see, basically, you could think that as a subset of the elements of A, such that P of X. Okay, this is a set theoretical reading, but actually in type theory, it is not an element of A. It is a pair made of an element of A plus a proof that P of X. Okay, and if you project such pairs, you will get exactly the set theoretical contents. Okay, but actually we have the two things. Okay, not one but two. So we can use this predefined type instead of defining our own type. So let us go. So you see this kind of definition uses the same constructs that were used for equality. So we have parameters, even two parameters, and so on. Okay, but it is easy to use. So let us see how we can do that. A pair, a tuple with two elements. What you have to do is just to count the number of arguments of the constructors, arguments which are not parameters, to be complete. So okay, let us see on this one, which is shorter. You have the constructor, and this constructor. Okay, this is the name. Okay, Jamlin. Not very important. Then the contents is you have X, an A, and then a proof of Px. Maybe I think the name is prod. I'm not sure. Yes. This one is simpler. But here you see pair. So this is the standard way when you want to talk about pairs. Okay, tuples with two elements. So here you have, okay, so the parameter, you have different parameters. Instead of A and P, you have A and B. Okay, and then, okay, the important part is here. How do you make a pair? Okay, so you have the constructor. Okay, it's called pair, and then you need to provide an element of A, then an element of B, and okay, and you get an element of the result. Okay, so this is rather easy to see, and for SIG, is that the same? So the constructor has a different name. Here you have an element of A and an element of B of P. Okay, the point that okay, you could say, remember, instead of A, you could say for all X of type A, then B implies. Okay, so you remember that the arrow is a special case of for all. In the case of SIG, you need to use the for all because X is used in the type of the second element of the pair. So another name for this is dependent pairs. Here for product, you only have non-dependent pairs, the usual ones, an element of A and an element of B. They don't, okay, the order is important, but the second does not depend on the first. Here it's different. You have a first element, but the type of the element of the second element, the type of the second element, sorry, the type depends on the value of the first element. So this is what it is specific. We call them dependent pairs or sigma types. Okay. In type theory, they use the big sig in the theoretical papers for that. Okay, but for for programmers, basic problem for us, you just write the following. You write, okay, so I take input C, input precondition, okay, and then the result will be a C prime such that next color CC prime. Okay, so it is easy to read. And the contents of this type is like before. My next color spec was something was constructed with the same with as much information, but specialized to colors and next color. Here I have something which is quite general. Okay, so let us put this on the top. So you can see that the refine here and there are very similar. Oh, sorry. Yeah. Yeah. Be careful. Okay, you see that I use exactly the same. Okay, okay. Here I am more lazy. Here I don't provide the name of the constructor. I could start to provide it. Actually, I am okay. I am like this part. I say, okay, for green, orange, and red, we will see later what is the answer. But for all the other cases, I say that okay, I have a precondition T, which is impossible to satisfy. So with 0 cases, so I just answer like this. Okay, and then for the first case here, I will say, okay, my answer, is orange. Okay, so let us go to this place. Okay, so I have, so first sub goal here. Okay, so I have my color. Okay, this is the whole thing. We can forget about it. This is the point is that C is now specifically green. Okay, so T is okay. So a precondition saying that, but actually I don't care about the precondition now because I know it is satisfied. The point is now to find an answer for this conclusion, and so here I have to provide 2 things. First, a color. This is my pair. Second thing, a proof that the color is related to green by relation next color. Okay, so first, so two stages. First stage, I say what is C prime, it is orange. And now I'm left to the second part. So you see that by saying that, C prime will be replaced by orange here. Okay, this is the reason why the next goal will be next color green, orange. Okay, here you see that it is a dependent pair. Okay, exit orange, and now so constructor, or I can find the exact name, but okay, and for the rest that's the same. Here I will say C prime, my answer will be red. If I try yellow, it will be impossible to prove the next goal. Okay, blue, shorter. Okay. Okay, now I'm lost. Impossible to. So you see that by construction, I am enforced to provide the good witnesses. Okay, so it is red. Okay, constructor. Okay, I can finish answer. So next thing, I can now project. So given the result of such, if I call only the first part of the pair, you see the pair here, okay? Okay, see, this notation here is actually kind of a general notation of Coq for talking about all inductive types with exactly one constructor. So actually you should write match. Okay, the real be match this with. Okay, the long fun, but then you have to remember the name of the you have to remember the name of the constructor. So match, you can write this way: match this with exist. And then I think there are, okay, this is here where I'm lost, but I think that Coq will complain if I am not, if I don't write enough wildcards. Exist what? Exist C prime and another wildcard. So the first wildcard, I think it is needed because sig is parameterized by A and other things, but one of them is implicit. So okay, so this is what is complicated to use with okay, rho C prime. Maybe I end. Ah, it works. Okay. Let's call it the real one. Okay. And okay. Usually you don't remember the name of the constructor and how the parameters are organized. So you just write this, which is more convenient. Okay. And this notation works whatever the name of the constructor. Once again, you can use it with the prod type we have seen before, or with a type with one constructor, but with, for instance, 3 or 15 arguments. Then you write parentheses and 15 X, Y, Z, A, B, C, D, etc. Parentheses, and you get it. Okay. So it's convenient. It's short. Okay. And now we can compute it. Again, you have a read. And as before, I could prove a correctness theorem, but basically it's useless because the correctness theorem is already contained in my definition. I can only return a result which satisfies the post condition by construction. Point to prove it. You can do that before, but the only interesting thing is to compute the result, so the simple result. Like here. Okay, so it's maybe time to, okay, I have only 3 lines to more additional lines, so maybe you can accept that. Okay, this one we have already seen. Now I will execute the command I presented to you before, extraction of okay, for the last one. Okay, it could be the other one, but okay. Now let us see what we have. Okay, Coq believes that this one could be useful, but actually we don't care. So we have our type of colors. We have nothing for about the preconditions. Preconditions are in the realm of predicates. It's not in the realm of OCaml, say. Okay, and here now we have our function, the function, exactly what we want. For green, it returns orange. For orange, it returns red. For red, it returns green. And for all the other cases, okay, we have an exception here, okay, produced by the extraction mechanism of Koch. Okay, so I will talk, I will add a number of little points later. I think it's time for a rest. Okay. Actually, I cheated a little bit. I will add something. Hmm. Okay, let me start.
Yes, this part is very advanced.
Hmm?
This part is very advanced.
Yes, a little bit, yes. But we'll see progress. Okay, so I want to show you. Okay, so first, okay, so before going to a little theoretical remark, what is? Okay, here. Okay, so I have also the other one, which is interesting. So I think that we have not sure the name we had. Next color CBC. Correction script. Oh, yes, we have script or we have, okay, it exists as well. Okay, so we have several versions. Okay. So actually, so I can perform the extraction command not only on the last one, but the previous one. And you see that you get exactly the same code. So remember, this one was okay, next call and next call CBC seed, for instance, are similar, are the same on the input arguments. The only difference is on the output. This one just a color. This one at the coq level returns a color plus a post condition. Okay. But now, if you focus on what is, if you forgot about pre and post conditions, they are the same. And actually, you can see that the extraction provides exactly the same code. Okay, so exactly the same function here and there. So the difference in approach is that for this one, so let us see how it was defined. Here, no, it was a wrong definition. This one, the right one. So for this one, I needed a precondition in order to be able to define it. And then, okay, I provided a simple input type. And then I had to prove separately in a second stage. So either for this one we can see the output, but maybe I could make a mistake here. I could write a blue here, for instance, or whatever. It would work as well. For the script, I felt more need to make a proof. But anyway, the point is that if I don't provide any post condition from the beginning, I have a precondition, but then it's better to prove separately that I have this theorem, correctness theorem. Second approach, I provide a post condition in the type, and then by definition, the code I will extract will satisfy this post condition. So okay, so two possible approaches which are equivalent. Either I have a simple type for the output, and then I prove separately this kind of theorem, or I provide a rich type for the output, which includes a precondition. Okay, so you get the same result. So extraction, basically, what is extraction? Extraction is just erasing. You erase whatever is in prop. For instance, here, okay, so you have C. Okay, C is a real thing. T, no, not T is something which is in sort prop, remove it. And for the output, what do you have? Okay, C prime. Okay, we keep it. It is a color, which is in the data, something which is real. And then we have another part here, which is a proposition. Erase it. Okay, so extraction basically erases everything which is in prop. And of course, you have to take care of the this kind of situation. Okay, and that's all. Okay. So it's the interest of this is that from a function which is defined in coq, and you can easily, or at least technically, you have the means of reason about functions defined in coq. For instance, you can define, we have did that. We had, for instance, the efficient reverse function on list. We could prove that the efficient reverse function on list, which is linear time, is equivalent to the quadratic time specification function. Okay, so we can use coq as a proof assistant. It is a proof assistant, so you can reason on functions easily. Technically, it's feasible, and at the end, okay, you have nice coq functions, but if you want to execute them in the real life, it's better to use a real programming language such as OCaml. And so you have a more efficient execution mechanism, and not only that, you can also completely erase what parts of the program which are just okay, things related to the properties of the program. Okay, like as you in your favorite programming languages, you can use assertions, this kind of thing. It is like, okay, adding kind of assertion mechanisms which are checked at compile time, not at execution time. But anyway, well, it's not clear. When you execute such a function, actually, when you execute it, okay, you also have, you may have computation on the propositional part, on the, so, and actually, what you know, actually, the point is that here you get, for instance, a pair. Basically, you get a color and a proof. But by the very elimination rule we have seen before, which says that it is impossible to make a real thing from a proposition, you know that this C prime cannot depend on reasoning. Okay, it only depends, the computation of this one depends only on C. It does not really depend on T. The value that doesn't depend on T. Maybe here it depends in some sense because, okay, we say that, okay, there is nothing, but if you just care about the real cases, the interesting cases, okay, this red here can only depend on the, okay, so the argument you had here, but it cannot depend on this part. Okay, we will see next a more interesting example with recursive programming. Here, the IDs can be presented on colors, so there is nothing to do with recursion. But once again, all the computations, the implicit computations at the propositional level have actually no impact on the output. This is why it is possible to erase the propositional part and say, okay, we don't care. Okay. So before going, oh, okay, you could do that now or later. Okay, maybe I will do that now while I'm at it. So I said that there is a very important elimination rule saying that it is impossible to make a set from a prop. Well, something in a sort set from something in sort prop. Okay, but actually we cheated a little bit. So remember, it looks at first like cheating. So I had this type, STL color. And what I used quickly was something like this, which said that I have a TL color order, so with 0 case, I can make a color. It is what I use here, actually, okay? So let us try. Okay, so I assume that I have something of type STLC other, which is empty, okay, actually. So let us introduce it, okay? I have this assumption, and I claim that I can make a color. Case T, or refine match T with empty, okay. Do you prefer the refine? Fine. Or exact, actually. Match T with end. Okay, I think it's clear. Finished. But you could complain because color is a set, but STL color is a prop. So actually, I eliminated a prop to get a set. Should be forbidden. So, but actually, there is an exception which says that if you have an inductive proposition with 0 cases, like this one, then you can do that. The reason is that actually you cannot really make anything. Okay, we can just say, okay, impossible case, something like this, but you cannot provide a real color. I could not say, for instance, this color is yellow or red or whatever. I just say, okay, it is a kind of impossible case, so it is allowed. Okay, actually, there is another exception. I can show you, which is, what do you have in my pocket? Oh, yes, for instance, this one is green. Okay, is green or is red, whatever. Okay, let us take is red. It's shorter. So is red. Okay, we call it exception 0. So this time, I don't remember the name of the constructor. E red prime. Okay. Prime, I think something like this. So you see that it is accepted. I don't have any. What do you have? Okay. Okay, so it's not very impressive. You just see that we could eliminate this one. It was allowed. But clearly, I have, but I don't have any additional information. The point is that in that case, actually, I don't really use anything. So I could make an answer. For instance, I could return blue. Okay, that's okay. It just means that actually I don't really use the information, the piece of information which is here is not that important. I say that, okay, there is only one possibility, and so what? Okay, so, okay, it is not, it would be very different if I have a predicate with 2 cases. So let us try. Okay, so this one is possible. So let us inductive. Okay, 2 colors, 2 calls. Prop again. Yes. But actually, this is not a predicate. It is just a proposition. I say, okay, I call it colors, but actually, it doesn't mean anything. Okay. say at T call 1, two values. No point to call them. Okay, so EV1. EV2. Okay, so let's try. Okay, so this is exactly like is red, but this time I have two possible values. Let us try to see what happens. Sorry. So expression 2. Okay, two vals. Okay, two vals. And then I should say this time it is either TV1. Okay. Okay. V2. I've written something else, for instance, green. Ah, plan. Okay. If I remove one, it will be accepted, but at least I have two. So the point is that actually I have a kind of Boolean information. I have two possibilities for proving that. And so there is an information here. It can be one or the other. I have a bit of information exactly in that case. At least as I have a small information which can be used to make a color, it is forbidden. Okay, so here, impossible. Okay. And it is the same situation, for instance, if you have a disjunction between two propositions. If you have a either blah blah or blah blah or another blah blah, okay, and you want to say, okay, if in the first case I want to return something, and for instance, okay, green, and the other case I want to return another color or another number, okay, but it is only in proposition I have A or B. I know I cannot use this information. Okay. Okay. So the point is that so you can count the information contents. Here I have a bit of information, but in Israel, I have no information because it is like a unit type. It does not contain anything. Okay. Okay, I just copy it here. Okay, so here I need to abort. Okay, so when you go to program extraction, you have to be aware of that. It means that in general, you are in a situation where you, at the same time, you manipulate real things like colors, numbers, trees, lists, whatever, and at the same time, you also manipulate proposition on them. Okay, so you cannot use information as you want. You can only use this kind of information, for instance, to prove things related to next color, for instance. Okay, but you cannot use this kind of information here or there to make data. Okay. So you have to be very careful about that. That said, usually, so I said that there are two approaches. An approach which is okay. The precondition here you need some proposition, but for the postcondition you have a choice between providing a simple output type or an output type plus a postcondition. So correctness by construction. So in that case, okay, you have to be even more careful. Okay, so that's all for the generalities because I don't want to be too. So the important point is that basically no information can leak from prop to set, and the zero case may look strange to some people. Okay, it depends on your point of view. You could consider that zero case is kind of infinite amount of information. But okay, you can say also that it is not what you get is not very useful, so it's also allowed. Anyway, there is a technical trick which allows us to avoid it. So it is we show it in at the beginning of the paper. I wrote with Dominique Larcher, Wendling on the Braga method. I will talk about this maybe today at the end or at least tomorrow. Okay. Bon. Okay. Usually people call the rule as the sub-singleton elimination rule. So sub-singleton, so singleton, it means it is okay, only one value here. So nothing can be exploited. And sub because the zero case is included in it. Okay, in general, it is accepted and easy to use. Okay, so now I will show you all this on a more interesting example, the example of even number. Maybe I have.
Sorry, it just try to understand. Go back to previous part.
Which one?
Is red implies cloud. Yeah.
This one.
Yeah. This, of course, this is a lemma which can be proved by.
Actually, I can. There is another way to prove it. Don't you? Okay. Good question. Yes.
You should correspond to correct meaning.
Okay. Another way of presenting it is the following. Actually, red is isomorphic to a predefined predicate of coq, which is called big true. Okay, so you can do that. Print true. It is an inductive-free proposition with exactly one proof. Important is you can prove it, but moreover, you have exactly one proof. And it says that, okay, if this proof is unique, and okay, so you could, okay. So from the logical point of view, you could say from true, I have nothing to, but actually it's not enough because here it is like a true with two possible proofs. And what I say is that, okay, the name of the proof is important, could be important. I cannot use it in this context because computationally, you could get on two answers. Here, with this one, you see that you can return, even if you use this information, you can return only one possible color. Okay, so it is basically like defining a constant. Okay, this exception one, the computational constant, contents, is to define a constant. You define a constant color. Okay, here your attempt to define two constants. It's like a kind of non-deterministic value.
Color is a set.
Color?
Color is a set.
Yes, color is in set.
So you can use this. They're not propositions. Even is red implies color.
Even if
this is not a proposition.
This no, it is not a proposition. Well, okay, what you can, if you want a proposition, you can have this one. Okay. Sorry. So it will not fail. Here I could return the TV2. Okay, go to TV one. Quite useless, but you can do it. Okay, it's only interesting for to understand what happens. No problem, because Tuval is itself a prop. So okay, so if, of course I took the same because
they are both provisions. So
yes.
a new provision, no problem.
Yeah.
With Israel, for example, it has color. Is it okay? This is a provision, but color is the same. How can you make arrow between two?
Okay, means that I am able to provide a color from any proof tree in this one.
From any proof tree and get a color.
Okay, yes. It's just really to with the functional eyes. For each proof tree of Israel, I want to provide a color. There is only one proof tree in Israel, so I can return only one color. So here I choose blue, I could choose yellow, but only one. Here I claim that I could make a color for each of these proof trees. So basically, if in a label, if two vals was in a set, okay, I could say, okay, I can return blue for this possible proof of two vals, which is a set now, and for the second one, TV2, I return green. Okay, so it's just a function, but this is not allowed because it is a prop. This is this rule which makes sense for extraction actually, because extraction means that okay, there is another computation which theoretically happen on proof trees, but I don't need to know the real contents of these proof trees. This contents has absolutely no impact on the real things, the list, the colors, the numbers, the whatever you want to compute with. Okay. So it is another realm which is which is invisible. Okay, this realm is invisible.
But can I change this color into a different?
Here, not. Yes, the same.
It's the same.
For NAT, you will say 2 and 15. Okay. Yes.
Yeah, I understand what you said. But still, it's not very intuitive. This kind of thing.
The thing which is not intuitive maybe is that usually when we talk about logic, we don't care so much about the possible proof trees. We are only interested in the result. This is provable. We are more interested in provability than in proofs usually. So this is why but in the framework of proof theory, we need to have a more fine-grained analysis. So proofs may become important from time to time. So yes. So this is an interesting discussion which could lead to S-prop maybe. S-prop is a space of proposition. Each proposition has exactly one. Even if you have different proof trees, you consider that they are all the same. So it's closer to what we have usually. But we cannot use them for anything. So and it is still an experimental feature of code. So I don't want to talk too much about it. But yes, it is. I think this is the source of the trouble you may have. Usually you are interested in provability. But here we see that for each proof, I may return a different color. So this is the difference, okay? If you say, okay, from the provability of two vals, I return a color. In that case, you want to say, okay, I need to return the same color in each case. So you could say, okay, I return blue and blue, but okay, anyway, Coq say no, you no pattern matching against this one if you want to make a color. Okay, so let us go to the even numbers to see, okay, maybe it may add some intuitive contents. So I go back to the first file, Coq number 8. So third part now. So I will present just a program for division by 2, which is a very simple thing. And I claim that I want this program to work only when the input is an even number. I don't want to define it when n is an odd number. Okay, this is my choice. I could make a different choice, but I want to make this one. Okay, so as usual, I define the small inversions for even, which could be useful. Okay, so remember even. You remember even? Maybe I can show you even, just to have it here. Okay. So you see that even has two possible cases: E0, which says that 0 is even, and E2, which says that if n is even, then S of n is even as well. Okay. Remember the shape of the proof tree, the proof like okay, just a column of even of E2, 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 and then you have E0. Okay, so now for a small inversion, I say that I have the case even 0, which is that, okay, this corresponds to this one. And so remember, I have one argument less, so I have just a prop. For even one, I have to consider it. So for one, no possibility of saying it is even. And for even SS, so I assume that I have the successor of n, and I say I just make a copy of the left-hand side of this one. Okay? So I have a parameter n, I get this one. So dispatch as usual. For 0, I return the first, 1 the second, S of Sn, I return this one. I can prove that if I have a proof tree of even n, then I have a proof tree of even dispatch of n. So which will be, according to n, either this one, or that one. Okay. Otherwise, you just use inversion, but the code would mean not very nice to show. So I'm more convenient for this. Okay. So let us now define this half function. So let us see how it is defined. So I have an input n. A precondition, so here I put directly it on right of the column. So I say that if n is even, then I can find a y such that y plus y is equal to n. Okay, basic specification of half, and here by extraction I will get a function which is correct by construction if I am able to prove this theorem to make this function like this. Okay, so again I will be in a half interactive mode. Why half? Because here what I really want to do is not to make an induction on n. Okay, remember, I cannot try to make a destruct on even n. This would be the easy thing to do. So people of Agda would say, oh, just consider the two cases, 0 and successor. But no. I don't want to do that. I want to say, no. Only n is available. Even n is available only when you reason, not when you compute. Okay, in some sense. So even will be, for instance, useful for proving things on the post condition. Okay. So n, I want to see what is n. And if you think a little bit, if you try an induction on n, you will have two cases. N is 0, or n is the successor of a number. And then we will be in a bad situation because it is not enough. What you want to see is basically this shape. So n is 0, n could be 1, another basic case, and n is the successor of the successor. So it is not something you can express just using the usual induction mechanism, because we see two steps under the n. You can make okay, it's more complicated. This way is clearly much easier. So okay, so I have this case, and each time I have to return a function. So maybe it may remind of the discussion we had just before. It's a function which takes a proof of even n and returns a pair y and a proof of the equality. Okay, so you can guess that the proof of even cannot be used to make the y, but maybe the proof of even could be useful when I go to prove this equality. Maybe we will see. So I have a function. So on each for each of these arrows on the right-hand side, I need to have a function from a proof of even n. So we'll see its type. Its type here will be of type even 0, type this even 1, type of this even of s of n. Okay, and I even can try to say what it is in this case. In this case, I will say, I want to make my recursive call. So let us see. My recursive call, I will call half with this n, which is structurally smaller than s of n. Okay. So we see here that the shape of my program is correct concerning the constraint on the structural. Okay, so, fine, structurally smaller. Okay. So I will call with n and the proof of, okay, but I don't know, so at the moment it's complicated. I don't know how to get it. We'll see that later. And then I will have to provide an element in this type. Okay, we'll see that later. And the point is that, okay, after making this recursive call here, what I will get is an element of this type. So it is a pair made of a result. So this is the half of n, and e, it is the equality saying that this result y satisfies this post condition. Okay, so at the moment I just have the general shape. N with 3 cases and a recursive call here, which is structurally smaller. This is only the thing I want to specify in this refinement. Okay. So I get 3 goals. Okay, 1 for each case. So okay, let us look at them one by one. So for the first one, I need to provide a witness y such that y plus y is 0. I know that I have this this is this EV, okay, but actually it provides no information, nothing especially interesting in that case. I am able to provide y. I say that, okay, the y I will answer will be 0. And then I will need to prove that 0 plus 0 is equal to 0. Okay. So exists 0. Okay, so I could activity works. Second goal. Okay, I need to prove a y such that y plus y is equal to 1. Well, difficult. There is no, okay, if I take 0, the result should be 0, and if I answer 2 or whatever, it will never be 1. Okay, so basically there is no good answer. Okay, I have this hypothesis here saying that 1 is even. 1 even, but basically 1. No, there is that's wrong. Okay, but here, so you could say, okay, what I could do is to invert this assumption, because we know that there is no cases for no possibility to prove even one. There is no proof tree for even one. And we can do that by small inversion, for instance, and that's finished. I will show you later another possibility, but at the moment, let us continue like this. Last case. Okay, last case is this one, and I have two goals. I have a goal which says, okay, please provide the precondition here that n is even, and when it's finished, please provide the answer for this case. So here I am in the precondition part, which says that, okay, I have EV here, this is this one, which says that S of n is even. I need to prove I need to provide a proof of even n. Okay, but once again, if I invert this one, and once again, my inversion function will work. Okay. Okay. So you see that actually the only way to prove this one is to have a proof of even n. So this is inversion, and so I can answer exact even n. Finished. Okay, and now let us see the answer I should provide for this case. So I have n, which is okay, even okay, and my recursive call here provide two things: some output y, which is suitable, which is a recursive call. So it is the half of n actually. And we can see that because I have the post condition on y, which says that y plus y is equal to n. Okay. And now I need to provide a new answer for S of n. So of course, the good witness will be S of this y. Okay. The successor of y, okay, should work. So let us propose this. Exist S of y. And then let us simplify. So now I have this equality to prove. So okay, let us compute a little bit. So we have the successor of something which is equal to the successor of something. Basically, we have a tactic which is called F equal, which just says that if x is equal to y, then f of x is equal to f of y. It is just a use of rewrite. We could use this one, which is convenient. So I need to prove that y plus s of y is equal to f s of n. I have this in my pocket. What could I do? Okay, for instance, I could rewrite from left to right this one. And here I'm a little bit provocative. I use the case because we just learned before that, you remember that equality is just a special case of inductive definition. So the case E actually just means that this n will be replaced by y plus y. Of course, usually you use rewrite in that case, but okay, just to show you that equality is just an inductive type as usual. So E has been replaced by y plus y, and now I have this goal, and you know that there is this theorem, this standard theorem saying that an S on the right can be put here. Okay, so I use this theorem from the standard library so that I could prove myself and reflexivity. Again, yes, here I was provocative. I could use the rewrite tactic, but here I am very, very basic. I use only the case. Okay, and reflexivity finished. Let us print it. I think it is not that large because of small inversion. If we use inversions of Koch, the result will be a little unreadable, but I think that here it is okay. Not that small, but not that large as well. So what we can see is what. So you see the shape which was here, okay. Okay, but presented in two stages, 0 and 1 which is the case when n0 is 0 here. Okay, so Coq planted way, and this is the S of n, which is the successor of n1, which is itself the successor of n0. Okay. And then what can we see? We can see, oh yes, for instance, this even here, inverted. And what is a little bit heavy here is actually this case, this case here and there. Okay, make a little bit of code. If I use rewrite, it will be simpler actually. So let us do this in the normal way. This. Still, okay, this is the inversion of EV. Okay, this is I think, but here you see typically, yes, EQ int, and if you call, I used it explicitly, but the EQ int typically shows that you used a rewriting step. Okay, just to show you that we had a function which is a little bit complicated to read, so usually we don't do that. But now what it is more interesting to do is to extract it. And here you get something which is very easy to read, which is exactly the function, the computational contents of half, which says that, okay, for 0, I return 0. For this one, so if n0 is 0, so basically if I have 1, oh, not allowed. Okay, so the precondition to use half explicitly here is I am not allowed to if I try to call half on 1 or on 5, recursively I will get the one case and I will have an exception. But it is a specification. The specification says that I can only use half when n is even. So it's okay. And for this one, okay, I make the recursive call and add 1. Okay, so just what you expect, and it is correct. So what is new if you compare with the previous example with colors? What is new is that it is here. The point is that for making my answer here, I use the result returned by the recursive call. I mean the simple result, the NAT, okay, and then for completing the part of the result, this part, the post condition, I use the fact that the recursive call had itself a post condition. So the post condition is transmitted and reused to compute this one. And what we could add actually, if you yes, what can be interesting? Print half is not that interesting, but let us. Do I have a proof of even 10? Maybe. I think I have one. Yes. Okay. I have a proof of even 10. I will use it. So let us compute. Half of 10, and if 10 should work. Interesting. I made a mistake. Do you see which one? Here Coq answers the half of 10 and even 10 is half of 10 and even 10. That's correct, but it's not what I want to see. I would like to see 5 and something. So why? Good exercise.
You didn't provide the answer 5.
Yes, I expect the compute to make the computation, but here the computation was blocked. So usually when a computation is blocked, you should have one reflex. Look at QED. And my mistake was I wrote, yes, here I wrote QED by mistake. So I said, okay, I have my function, but I don't want to, I will not be able to compute it. So let us use define now. Okay, so okay, so I see the result. So exist. So this is the type is not very important. I have my 5 with this one, and I also have the proof that 5 is the half of 10. Here's the proof that 5 is the 5. So you see that the computation, okay, but it makes the full computation. I'm not that interested in this one. I would like to block this computation. Is it possible? Yes, with the let. Okay. So I will do this in 2 steps. First, eval lazy, just to want to see if lazy will be more. No, I think no, because okay. I think I will have the same result because actually I want to go, okay. I ask lazy in maybe. Yes, okay, so same result, so no difference. But now let us define the definition. Okay, a definition raise the half. Raise the half, which takes n, a proof. Well, it should guess of n is even. I am lazy, and which returns. So let alors the result half or y, and I don't care on this one. So the half of n and EV in y. Okay. Now let's see what will happen. So result this time. Ah, but yes, there is nothing to see actually. So I don't know, maybe Coq made the computation, but I can't see it. So if I want to be sure that Coq don't make the computation, I could use this one. But we cannot observe that. The point is that actually, okay, so what I want to point out is that the following. For computing this y, I don't need the canonical form of the proof. The proof could be, the proof can be any application of theorem, but actually, I guess that this, yes, actually, I guess that this plus, because I understand why we had something complicated. Let me check. Much. Bref, I know. Yes. I think that the guilty guy is here, because it is a theorem with a QED at the end, so Coq is not able to compute with it. So it just confuse a number of things, but at the end it is not able to use the fact that plus S and M, okay, what is its computational content? So actually Coq makes a kind of big proof tree which is not completely computed, but at the end, my guess is that if everything is transparent, what we call transparent, and I think that's only it is this one. Don't think there is any other. Yes, also even inv. Even inv finished with a QED, it could be dangerous. I don't know. So as far as we have QED in the proof part, Coq is not able to finish the proof. It makes a proof tree, which may be big or not. But the point is that in order to know the important result Y, we don't need the finished computation of this part. Actually, if Coq was able to finish the computation, I guess it should be just the proof of this one. The canonical proof of this one is basically a graph. So the finished proof should be, but I don't want Coq to make the computation. Okay, he performs something here, but it's not important. What is important is this one. For this one, whatever the proof of this one, okay, yeah, I know that it is a proof that Y plus Y is equal to N, and that's all. Okay, so we can extract and so on. So here we, okay. In some sense, if I compute this, the same will happen with Coq when I use this command here, which says that, okay, compute only the first part of the pair, only the first projection. For the second one, I don't care. You don't need to compute it. So with ZD, normally Coq should not even try to compute it. Okay, so that's all for the Coq 8 devoted to inductive relations and a little bit of extraction at the end. Now we will see extraction used in compilation. So we'll talk about certified compilers. Well, it's a very small compiler. So this one. Okay, so maybe I printed a little bit last time, I'm not sure, but anyway. Okay, so we go a little bit into more details, not all of them, because, okay, so there are some exercise to do, so this is your work. So I take a little part of the while language, actually only the part devoted to arithmetical expressions. So I have this type, I don't need the rest. So I have a notion of state to define its semantics. Remember, I can define some examples. This is better with example, by the way. I prefer to keep the word definition when it makes sense for the main, okay, for the core of the demo, and examples are just to make test, for instance. Okay. So my get function, my evaluation for the definition, for the denotation of semantics. Okay. Okay, and now I want to compile these ASTs into a sequence of instructions of a small assembly language. Okay, so I take a very simple stack-based assembly language. I call it ALS, assembly language with stack, something like this. Okay. As usual, I define a type and I will define its semantics. So this is the instruction set. So I have an instruction called push, which expect it to push a number on some stack. So it has one parameter which is the number I push. So fetch, I think will fetch something in the memory. I have my machine will have two parts, a memory where I can fetch and a stack where I make some computations. So fetch, okay, and then add, sub, and null. Okay, so instruction which operate on the top of the stack, and the code will be just a list of instructions like this. Okay, we'll see some example later. Okay. Usually for an assembly language, it is an imperative language, and the good thing to do is to define an operational semantics, but here the language is very simple, so I am able to define even a denotational semantics. So I take the simpler semantics that I can. Okay, so in this case, I will use this one. Okay, so what is semantics? So the semantics will be defined with a stack. Okay, it's a kind of state. So a stack will be represented by a list, and the idea is that this is the empty stack. Then I pushed 2 on the stack, and then I pushed 5 on the stack. Okay, so you read the stack from right to left. Okay, the bottom of the stack is on the right. Okay, this is my stack. And then I have a push function, which is just very simple. If I push n on the stack, okay, so I just return the stack with n on the left of the stack. Okay, what else? Okay, then I need, yes, next I will provide the semantics of each binary operator. So what is the semantics of addition, etc. Okay, so I will define it in a general. I will take because all of them are binary operators which works in the same way. They take the 2 values on the top of the stack if I have them, for instance. Okay, so let us consider. So I have a parameter which is a binary operation, which is a function from nut to nut to nut, and then I have something which takes a stack and returns a stack. Okay, so if my stack S has at least 2 values on top of it, so A and then B, okay, then I will compute my operation OP on A and B, and I will return the stack where A and B have been removed and OP AB has been put on the top. Okay, and in all other cases, okay, I could, okay, in OK assert false, something like this. I have no exception mechanism in Coq. I could, with what we have seen before, define this with a partial operation, but here I was a little bit lazy. I just said, okay, in the other cases, I return an empty stack. Okay, yet another way, or another possibility would to make an option type. Okay, in that case, I am able to recognize statically if my stack has a right. But in that case, I should return an option here, some here, and here a none. It would be yet another option possibility. Okay, so now what is executing a code? So a code No, not a code. A code will be later. Now, I just compute the effect of one instruction, I, okay, a basic assembly instruction, I. So it takes I take a state, and I return a function from stack to stack. Okay, so if I is push, okay, then I return the function push n. You remember, actually, all my functions are of type stack to stack, push and exec. Okay, so this is more convenient to see this execution as something which takes I and S and returns a function on stacks. So for push, it is push n. For for fetch, for fetch x, I will push the value obtained with a get of x on S. So the x of fetch corresponds to an identifier, as usual. Okay, so I will use the machinery I had before on states. Okay, so I am able to get, so x, you understand it as an address. Okay, and I get the value in the memory S at address x, and then push it on my stack. And for the binary operators, so I use my previous function, opbin, but op is the function plus, which is called not add in the library. For minus, it is not sub, and not mul for the multiplication. Okay, so you see that executing an instruction from a state. Okay, and now what is the semantics of the code? It is just repeating exec I. Okay, so executing a code. Remember, it is a list of instruction. Okay, and again, I have a state, and I return. Okay, so here P is my stack. I don't want, okay, P, so P like the pile in French for stack, but I already have the S for stack, so I had to find another name, so I chose P. Okay, so what I say that if the code is empty, so I finished the execution of the code, then I return P. Okay. And if my code is made of an instruction followed by C prime, so first I will execute I on S and P. Okay, so I will get a new stack, P prime. Okay, and then I will continue the execution starting from P prime and with the rest of the code. So this memory state, okay, you can see here that in this, with this instruction set, this instruction set use the memory, but it does not modify the memory, okay? Because I have only simple expressions, and you know that we have pure expressions in this case. So computing an expression does not change the memory. It would be different if I had things such as x plus plus, in my expression. But I have pure expressions, so the memory has no reason to change. So my state is just an invariant. Okay, so S will not change. It is just the same parameter at each time, and but what change is the stack. And that's all. You could also have a different. You could use a composition of to express this fixed point here. Okay, because you could see that it is a function from stack to stack, and basically for nil we could say that it is the identity function, and for this one it is the composition of the semantics of I with the semantics of C prime. Okay, but okay, this code is just another way of saying the composition of these two functions. Okay. And then, okay, this is the semantics of the code. And now I would like to go to compilation. So this is okay, but before that, a technical lemma which can be interesting to use later, which say that if I have a code C1 and a code C2, I can consider what is the effect of C1 followed by C2. So this plus plus is just an infix notation for the append operation on list. Okay. So what I say is that, okay, but if I execute P1 and you return P2 using C1, and similarly executing C2, I go from the stack P2 and get the stack P3, then, okay, that's exactly the statement you expect. So nothing difficult here. Okay. And, difference. Ah, yes, it is another version of the previous one, which is more intentional in some sense. That's funny. It says that the function, this function, say here we have both. Yes, okay. It is a similar theorem, but expressed with less, okay, with only one P here. Okay, now here I had a P1, P2, P3. Okay, bon, okay, so this is not the main topic for now. So, okay, I will leave this second version of the theorem here for later. So let us go to the interesting part, which is compilation. Okay, so what I say is the following: is that I am given an AST here, A. I want to provide a code, so a sequence of instruction, and it is rather easy. So I consider all the cases for the AST. So if n is a constant, okay, then the code will be just the list made of push n. Okay, so a list with a single element. Okay. Similar for a variable. For a variable, the code will be fetch x. Fetch the contents of the address x. Okay. And then, okay, the interesting cases are for binary operators. So imagine that you have the plus of A1 and A2. So first I will compile A1, so the AST A1, I will get some code. So what I do is that I compile the code of A1, okay, and I append it with the code for A2 here, and at the end, I say, okay, now apply the instruction for addition. Okay. It's just okay. So the mechanism, you know, if you know a little bit of stack machines, okay, and that's the same for subtraction, multiplication and subtraction. Okay. So this is the code you will get, and now we can play. So here, this is an example. Okay, so here I have a basic AST saying that adding the value 2 to x. So x is was defined earlier. Okay, is some address in the memory. Okay, here I want to I reuse the previous one, and then I will subtract 9 from the previous. Okay, so this is 2 plus x intuitively, and this one is 9 minus 2 plus x. Okay, so I have two AST here. So let us compile them. So I compile the first one, and I get what you expect, which is, okay, so for this one, so push 2, then fetch, so x is represented by the value 1, okay, so fetch what is at address 1 in the memory, and then add, okay, so you compute x plus 2, okay. So this is an instruction, you get no computation at the moment. So now let us compile the next one. So 9 minus 2 plus x. So you get it here, maybe. So again, you push, compute, no, it is not, let us compile it now. So you push 9, okay, then you push 2, then you get x, so it is address 1, you add this one, so you compute 2 plus x, and at the end, you subtract, so because basically here you should have 9 and the result of 2 plus x on top of the stack, okay? Okay, now we can execute the compilation of our code. So I have to provide a state. So S2, okay, the S2 says that x has a value 3. Okay, we can check it. S2, yes. I have a 0 for, okay, I don't care, I don't use this one. And I have a 3 at address 1, okay? Okay, so I have a 3, so I should get 2 plus 3 should be 5 for this one, so I should get 5, I guess. Okay, no, first the constant 2. The constant 2 should return 2. Yes, so I get at the end a stack which contains 2 at the top, okay? For this one, I guess I should have a 5, yes. And for this one, I should, by execution, I should get 9 minus 5 should be 4. Yes. Okay. So I can place, this is the pleasure of a computer scientist, is they can make tests, not only prove theorems. Okay. Okay, now let us go to the interesting part, which is proving that my comparator is correct. So this is your exercises, but at least we can state the theorem, which is the following one. So given any AST and any state, okay, no, I start with the last one. This one is the auxiliary one I need to prove the main statement. The main statement is the following, which says that given an AST and a state, if I compile A, so I get a code, I execute this code in my state S, starting with an empty stack, then I will get at the end a stack with exactly one value, which is the evaluation of A. Okay, so you see the statement is exactly very simple, okay? But you cannot prove it directly. You need to, because this statement, once again, is only for initial empty stack. So you remember for what we have done before that it will not be enough. You need to reason on any stack. This is why you have here a more general statement. Okay, you read it later, but basically, yes, I have the same P, but at the end I execute. Okay, you will read the statement, and we can make the proof. So basically, okay, I think. Maybe 10 minutes to perform the exercise if you are okay, if you are trained to this kind of thing. Okay, and that's all. And then at the end, okay, so I could prove that I just prove that my compiler is correct, and so I can extract it. Okay, so here are additional exercises if you want. Okay, so but I think I'm not sure that we can do that now. Oh yes, okay. Okay, here is my certified compiler in OCaml. So here I chose the first style. I mean the style where I have a coq which returns a simple type, okay, which returns a type, the type of code, okay. I could make something different and have something which I want to return a compiler such that this property. It would be probably more complicated. Okay, but okay, it's an attempt. It is also an option. But anyway, I am sure that this code, provided I use it, okay, in that case, it's that simple because I have no precondition. I have no precondition. So in all cases, I will return, each time I call it with an empty stack, it will return the result, which is defined by the semantics of the source language. Okay. And then concert is just another example, a little bit more complicated. Okay, so I think we can stop this today. So I had I prepared some material on more advanced extraction using what I call the Berger method. But okay, this will be the topic of tomorrow. Okay. Thank you.
Oh, no.